It seems I had some issue with my recording this afternoon, so let me re-record today's lecture. Previously, we talked about discriminant analysis, where we model the joint distribution of x and y as follows. Y is a discrete random variable taking capital K different values, so we model the corresponding probabilities as P1, P2 until P sub k. And given y is equal to k, we model the p-dimensional feature x with a distribution function f sub k. When we try to form prediction at a new feature with a new feature x, what's relevant is to calculate the product of pk times fk, and then we rank them from for all the capital K different products, and then predict with highest value. So that's equivalent to compute the log of that product, known as the decision function d sub k. So d sub k of x is equal to log pk plus log of the distribution function fk evaluated at x. And we can further subtract any constant which is irrelevant to k, because all we care is the order of those capital K values, and that will help us to predict the y value for x. And depending on how we model the p-dimensional feature, meaning how we specify f sub k, if f sub k is a normal distribution with different mean, different covariance matrices, then that's known as QDA. If we restrict the sigma to be the same, that's called LDA. And if we further require the p-dimensional feature x and the corresponding distribution functions are all independent of each other, meaning the joint distribution on this p-dimensional vector x is equal to a product of individual distribution over the p-dimensions, and that's called a naive Bayes. And here we keep adding more stringent assumptions on fk, and the purpose is to restrict our model and to avoid overfitting, and this is common when p is very large, the dimension. So here's a QDA. In QDA, we model the p-dimensional feature x in every group as a multivariate normal distribution with a mean vector mu k, which is p-dimensional, and a covariance matrix sigma k. And what's relevant in the computation is actually the inverse of the covariance matrix, and sigma k inverse, often known as the precision matrix. Here I denote each of the entry in the precision matrix as theta. And the density function for such a multivariate normal takes this form. Here I want you to picture the quadratic term inside that bracket, which is equal to a row vector times the matrix, which is the precision matrix, and times a column vector. So that will give you a number. If you take a log of the PDF, you're going to get a quadratic function of x, and this is why, and this is known as the QDA, quadratic discriminant analysis. If we further require all the covariance matrices are the same, equal to sigma, and then you can go back to look at the calculation for the decision function. And first, we don't need to compute log determinant of sigma, because that's the same for all k. And further, we can look at the first term, that quadratic term, and we can expand it, and you're going to find out x transpose sigma inverse x. Again, it is a constant irrelevant to k, so we can drop it. Then you're going to find out the decision function is essentially a linear function of x, because x only appears once. So this is why this is known as linear discriminant analysis, LDA. In practice, we can estimate the common covariance matrix sigma by the so-called pooled sample covariance matrix. It involves a double summation. The inside summation is a contribution of is sort of the covariance for each of the small k group, and then because we assume the covariance matrix is the same, so the outside summation is just aggregate sort of the within class covariance. We sum them all together across all the k groups, and then do a proper normalization 1 over n minus k, and that's our estimate for sigma. Previously we talked about what would happen if sigma inverse does not exist, because the rank of sigma, based on the calculation, and sigma is a p by p matrix, and the rank is at the most n minus k. So if our p is really large, and for example, for that digits data, p is 256, if our sample size isn't that large, then our sigma hat may not be of full rank, so we cannot take the inverse. And it's not difficult to fix this. One is just to add Lda times the identity matrix, and here Lda is a small number. Or we can just compute this so-called generalized inverse. And what's generalized inverse? Assume dimension p is 3, and for sigma it is a symmetric and semi-positive definite matrix. If its rank is actually 2, not 3, that means sigma hat admits the following sort of singular value decomposition form. It is equal to U times a diagonal matrix where D1, D2 are strictly bigger than 0, and then U transpose. So what is U? U is the rotation matrix. For example, here I show you a picture. Suppose we want to rotate a vector v0 to v prime by an angle theta. That rotation, meaning the new v prime, is actually equal to a matrix times the original v0 vector. And that R matrix is a rotation matrix in 2 dimensions in the sense that every column of R is going to be of norm 1, and they are all orthogonal to each other. And for example, in this case, we're going to, and the original coordinate is an x0, y0. Then we can just do a rotation, change to an x prime and y prime. And that if that rotation can be accomplished by just multiple every vector 2-dimensional by this rotation matrix and R. So that's the U here just denotes some kind of a 3-dimensional rotation matrix in the sense that if we're going to rotate our coordinates in a 3-dimensional space, then we look at our data, and again in the 3-dimensional space where the first dimension is going to have variance D1, the second dimension is going to have variance D0, and the third dimension is going to have variance 0. Means at the third dimension, all the data points going to equal to each other. So there's no variation at all. And that's somehow called the null space. And we cannot, the problem is when we take inverse, we have to deal with 1 over 0 and in the original space. But we can just ignore the third dimension, only and do the inverse for the first 2. Why? Because in the third dimension, there's only, everybody takes the same value, no information there anyway. We just ignore it. Previously, we also talked about the Reduce To Rank Lda. Here, all of our discussion is based on the assumption that our P is really large, is bigger than K minus 1. K is the number of classes. And so we can consider this simple case. Suppose our sigma is identity. Then you can go back to look at what is a discriminant function or decision function d sub k. It actually equal to this. The first term is basically the ordinary Euclidean distance between the point x to the case center mu k. So the x only appears there. It is just the L2 distance to the case center. Because what's relevant is only the distance to that case centers. And we know that 2 points determines a line and 3 points determine a plane, and k points determine a sort of a k minus 1 dimensional hyperplane. If we move the origin to this plane, then they basically form a k minus 1 dimensional subspace. And what I want to say is that you're going to find out when you operate your LDA in the original p-dimensional space, is actually equivalent to operate your LDA in a lower dimensional space, k minus 1 dimension. There's no loss of information, everything is the same. So here's the intuition. For example, we have data from 2 groups, and the data original dimension p is equal to 2, But because a binary classification problem, k is equal to 2, so k minus 1 is only one dimension. In this case, you can find out our decision should be the same if we project everything to this horizontal line. So we have our center here and center here. So the LDA in the original two-dimensional space should be exactly the same if I project our data to that horizontal line and operate LDA in a one-dimensional space. Now, what if the covariance matrix sigma is not identity? So for example, let's look at the data shown in these two pictures. So the data are the same, the blue and the red. So here's the center of the blue points, and here's the center of the red points. So we connect the center of the so this line, we connect the two centers. Well, does that mean we should project data to this direction, like what was shown on the left? It is actually not optimal. It's optimal to project this way. And why? Because when the covariance matrix sigma is not identity, what we need to do is we first have to rotate our coordinates and do some stretching, and then make the covariance matrix in this transformed space to be identity, and then do the projection. So in this case here, you can see that we should really rotate our coordinates, the original one like this. We should rotate it to be the new black coordinates, and then you can see now we probably need to also scale one of the coordinate to make the data clouds look like a sphere and symmetric, and then do our projection. So this direction and is the right direction and to project. I give more detailed expression for this for this reduced rank in the notes. Here, just I just want to give you a rough idea of how to operate this reduced rank LDA, and you don't need to follow all the tidbit and details of this matrix calculation. So suppose we have a test point x star, and we grab our output from the training, meaning we have learned the mix and weight pi k, the k centers mu k, and a shared covariance matrix sigma. So what we're going to do first is to find the rotation matrix to sort of normalize, scale the data. In the one-dimensional case, we should scale by times our data, multiply our observation by 1 over standard error, right? But in the matrix version, we do something like sigma minus a half, which is basically the A matrix. And then we apply that A transformation on all the data points, and then we calculate what is the projection matrix, how to project data to that space spanned by those K centers, and then operate our LDA in that reduced space. And just in case you want to know how we're going to project data to that space with the K centers, we can just run a linear regression, because the K center, you can you can think about this as a design matrix with k minus 1 columns, and every column is a p-dimensional vector. So they span the k minus 1 dimensional subspace. So that's our design matrix. You just run a regression of every x onto this design matrix B, and the fitted value would be the projection to that k minus 1 dimensional subspace. And so the same subspace is actually going to arise in some supervised dimension reduction method. We have learned the dimension reduction method like PCA, which is unsupervised. You only operate that dimension reduction algorithm on X. You don't need to know Y. Y doesn't even need to exist. But for supervised dimension reduction, we do know Y, the label in this case. So we want to find a direction such that if we project our data onto that direction, so we get a bunch of one-dimensional numbers, and then we want to see the data are well separated. For example, for this picture on the left, the data are in two-dimensional space, and they are from 3 classes. And here we list the 2 directions, the best direction, which is the one on the left, and the worst direction. Here, and we know the right one, the direction on the right is correct, because once we project data there, we see the 3 groups, green, blue, and red, they are well separated. And so how are we going to solve for these directions? First, we have to define what do we mean by points are well separated. It basically means that if we look at the mean of the 3 groups, then they are far away from each other. But meanwhile, we look at the data points that are from the same group, they should be tightly around their mean, meaning they're close to each other. So they can be formulated as the following. We wanted to, I wanted to maximize the following ratio. We wanted to maximize the ratio, which is the ratio of the between group variation and the within group variation after projection. So suppose the direction we're trying to solve is this A. A is a vector in RP, and turns out this ratio, after we project data onto that direction A, this ratio can be written and can be computed this way. So it's a ratio, and the numerator and denominator are quadratic terms involving a matrix B on the numerator and a matrix W in the denominator. So what's B and W? And the W stands for within class variation, which is the same as the pooled sample covariance matrix we mentioned before. And so we have double summation. The inside summation is the variation of every xi to its own class center, and then we accumulate those variation over the k classes. So that's the within group covariance matrix. And B is the between group covariance matrix, which measures how far the class center away from each other. So here the mu k hat is basically the sample average of the p-dimensional points, and sample average of points from the case group. And this mu hat bar is the average of those capital K centers. And you can sort of think about the W and the B in the following way. First, we have the following trivial equalities. Every observation xi, which is a p-dimensional vector, can be trivially represented as x1 minus its own class mean and plus its own class mean, right? So now you can think about the within class variance W is the sample covariance over those purple points, and the between class and class covariance matrix B will be the covariance among those blue points. So how are we going to, once we calculate B and W, how are we going to maximize this ratio? It is equivalent to specify our maximization this way. Okay, so without this part, that's the ordinary kind of PCA type of problem, or just ordinary eigenvalue problem. But this is a generalized eigenvalue because we wanted to maximize some quadratic function involving A, subject to a quadratic function constraint in terms of a quadratic function on A. So the trick is to sort of decompose our W as a square root of W and allocate that to A. So we do a transformation, and you're going to find out this condition becomes just the norm square of another vector B. And then we rewrite this objective function. So the problem becomes maximizing some quadratic function involving B, a vector, subject to this constraint that this vector norm is 1. And that's just an ordinary or classical eigenvalue problem, and we know how to solve it, the solution of B will be the first eigenvector of this matrix. So here's how we're going to solve those FDA directions. We first retrieve